Good morning, all. My name is Pushpendra Kumar, and I am going to present the paper entitled Bone Graph Model Based Control of a Wheeled Mobile Robot, paper ID 104. So, we start with the introduction of mobile robots. So, here we focus on mobile robot with wheels because mobile robot can be flying robot or underwater robot. So, we are focusing on mobile robot for application of grounds and which are being used in many areas such as in industries, in military operations, in space missions, and so on. When dealing with mobile robots, their dynamic and kinematic modeling is important because to develop their control and to obtain a desired motion of robot, it is important their dynamic and kinematic model should be analyzed. Most of the controllers are based on the kinematic model, but an efficient control can only be realized by considering the dynamic model of the robot. And to ensure the robustness of the controller, which can deal with many disturbances, it is interesting and it is important also to develop the model-based control strategy. From the literature review, it is identified that a complete multi-domain model of a mobile robot dynamic with its model-based control is missing. Therefore, in this work, a mobile robot has been analyzed and its dynamic model is developed considering its multi-domain parts. Here, multi-domain means like we deal with the multi-physics like electrical, motor, wheel and ground contact dynamic, longitudinal, lateral and yaw movement of chassis. So it is a electrical as well as mechanical system. So we need a multi-domain model of the system. So we start with the kinematics. So here we can see this schematic diagram of the robot. This is the left wheel of the robot, which is rotating with omega 1 velocity, right wheel with omega 2 velocity, and the linear velocity of left and right wheel is V1 and V2. At the center of these two wheels, we consider the center of mass Cm, which is at equal distance from the wheel, L and L. A frame, body fixed frame is attached to center of mass, whose axes are XB and YB. And along the XB direction, we have this longitudinal velocity of the robot. And the orientation of robot theta is with respect to the x-axis of the ground fixed frame, which is an inertial frame fixed to the ground having x and y axis. So the relation between this body fixed frame, which is moving with the robot, and the ground fixed frame is given by this relation, where these are the velocity in inertial frame, velocity in body fixed frame. And this R is a rotation matrix, which is defined in terms of the orientation of the robot theta. As we know, this XB velocity in longitudinal direction is given by V. Here we can see this is a V velocity, and we assume that there is no motion in Y direction along the Y axis. Velocity is 0, so it is 0. By putting these two values, we get the velocity in x direction with respect to inertial frame and y velocity. Okay, so also we can calculate this linear velocity of wheels v1 and v2, which depends on this theta dot. Theta dot is nothing but the omega. Sorry, theta dot is angular velocity of your robot. Okay, and further this v1 and v2 can be calculated using the angular speed of wheels. This is omega 1, like r omega 1 will be v1. Now come to dynamic modeling. To model dynamically, we use a graphical and power-based modeling approach, which is known as bone graph. So This approach is based upon the exchange of energy phenomena between systems of various domains. Because energy is common in all the domains, so it is very much suitable when we are dealing with multi-physics systems like having mechanical, electrical, thermal, and hydraulic components as well. The major benefit of bond graph modeling can be described as follows. First one is graphical and useful for the multi-domain system. Since it is graphical, it provides more insight of the system. And systematically, by following the graphical property, we can model any complex systems and we can derive its dynamic equation. The theory of control and monitoring is well developed in bond graph, so we can apply bond graph for control and fault diagnosis purpose as well. So in bond graph, for example, we have two systems of different domains, say S1 and S2. So if they are in physical contact, they will exchange energy between them, and this exchange is represented by a power bond represented by half-headed arrow, which carries two power variable, effort and flow. The multiplication of effort and flow gives us power. The direction of effort is represented by putting a vertical stroke on the arrow. So this is the effort direction, and in the opposite direction we will have flow. Similar. So if this system is represented by some dynamic element, there are some bond graph elements, like I represent a inertial element in bond graph. It can be mechanical mass or electrical inductance. So from this we can calculate its dynamic equation, like this element is taking effort and giving me back flow. So this flow will be equal to 1 upon I integration of this effort. Similarly, there is capacitive element, which can be electrical capacitance or mechanical spring compliance. And we can see that this element takes flow and give me back effort. So this effort EC will be 1 upon C integration of flow. So using that concept, we develop dynamic model of this mobile robot. So we start with this left wheel motor. So for example, we give some voltage to the motor U1. So this voltage, due to this voltage, some current will be generated I1 in the left wheel, and some energy will lost in the internal resistance of the robot, internal inductance of the motor, and remaining energy goes further, which will lead to angular rotation of the wheel omega 1. Some energy will lose in the viscous frictions and in the rotary inertia of the wheel, and remaining we have energy goes further. So here we will have r omega, velocity omega is there. If I multiply with r, I get the r omega. But this r omega will not be equal to the v1 velocity if there is some slip. So this is the energy lost in slip, wheel slip. And due to this dynamics of left wheel, we get force generated by the left wheel F1. Similarly, from the right wheel, we get the force generated F2. This F1 and F2 force is transferred to the center of mass of the robot, where the linear velocity and the angular velocity of the robots are considered. Okay, so this C with full head arrow, it represents a sensor. So this sensor will measure the velocity of the center of mass speed. Okay, this will measure the velocity and orientation of the robot. And if we want to calculate in the inertial frame, we use this transformation sin theta and cos theta we get in the inertial frame. Now control. So the developed bond graph model is used to develop a model-based control strategy. So here we have this mobile robot dynamics. We use the inverse dynamic of robot. In fact, in this dynamic, we give voltage to motor and we get position and orientation of the robot. But in inverse dynamic, we give position and orientation of the robot and we calculate the voltage, motor voltage, which we apply to the robot which we want to control. So this position and orientation are calculated using the error signal, and this PI controller is used, where the desired position and orientation is compared with the actual position and orientation. And this error signal is sent to the PI controller. And from this PI controller, we can calculate this X bar, Y bar, and theta bar, which we can use for our inverse dynamic model. So how we develop this inverse dynamics? So here, this is the model-based control strategy, where we first of all we calculate this X bar, Y bar, theta bar, which are coming from the PI controller. And for PI controller, we provide this desired value. So here we provide some desired values of X, desired value of Y, desired value of theta. And from this PI controller, we are able to calculate this X bar, Y bar, and the theta bar from the PI controller. Once this X bar, theta bar are calculated, from the bond graph model, the energies flows in the arrows of these bonds, and finally we get the output U1 and U2 voltage, which are required to control the robot here. Okay, so these U1, U2 goes to our main model. So once the bond graph model is developed, we simulated it in a software called Symbols, and the symbol software is dedicated for bond graph modeling. So once you draw the bond graph model of the system, its dynamic equations, differential equations, are automatically generated. However, we can calculate these equations systematically, manually, by using the graph flow, but it is easier in software, it is automatic. So from the simulation result, first we check our bond graph model, and we don't apply any control to check whether the model is correct or not. We give same voltage to both the motors, and this is the angular velocity. Of course, those angular velocities will be same when we give same voltage. And we see the trajectory, and the robot moves in X direction only. There is no change in position in the Y direction, which is an expected result, because we are giving same voltage to both wheels. They will move in straight X direction. And another, we give 10 volt to the left motor and 50 volt to the right motor. So there is a difference in angular velocity. We can see omega 1 is less because less voltage 10 is applied, and omega 2 right is more because we apply more voltage, 15 volt. In this case, we see that the trajectory, it is curved trajectory, because there is a difference in angular velocity of two wheels, and which is an expected result. Now we check our controller, model-based control, and the aim is to regulate the position and orientation of the robot. The desired position and orientation of the robot are taken 5 meter, 3 meter, and 1 radian. So from the results, we can see that in the model-based control, the robot gets settled at desired 5 meter position in X, and 3 meter position in Y, and 1 radian angle in the orientation theta. So the controller is working well. So these are the conclusions of this work. A multi-physics graphical model of a mobile robot is developed, which is multi-physics. Of course, we have electric motor and a mechanical wheel ground dynamics, chassis dynamics, including longitudinal, lateral, and yaw directions. A bone graph model-based controller is developed to regulate the position and orientation. The developed model is first verified through simulation without any control, and we got the expected results, and then the developed control strategy is verified. And from the control results, it is showed that the developed model-based control regulates the robot to a desired position and orientation. And in future, it is interesting to consider faults in the actuator to apply some fault diagnosis technique, because bone graph is well utilized for the fault diagnosis purpose. Thank you, and your questions and remarks are welcome. Thank you very much.